Hi guys, welcome to Smart Alex Coaching. In my last video, I talked about the connection between the function f of x with its first derivative f dash x and the second derivative f double dash x. And I pointed out that by solving f double dash x is equal to 0, that doesn't guarantee us a point of inflection. It only gives us a possible point of inflection. So what I'm going to do in this video is I'm going to go through that point in a little bit more detail. So let's consider the following two functions. The first function on the left-hand side is a cubic curve, f of x is equal to x cubed. And on the right-hand side, we've got a quartic curve, f of x is equal to x to the power of 4. So for the first curve, our cubic, f dash x is equal to 3x squared and f double dash x is equal to 6x. For our quartic curve, f dash x is equal to 4x cubed and f double dash x is equal to 12x squared. For our cubic curve, if we solve f double dash x is equal to 0, we're going to get 6x is equal to 0, and solving that, we have x is equal to 0 as our solution. Now, what you observe here is that for this cubic curve, by solving f double dash x to be equal to 0, we get the solution x is equal to 0 that corresponds to the point of inflection. You can see on the left-hand side, the curve concaves down. On the right-hand side, the curve concaves up. And since there's a change in concavity at x is equal to 0, we say that we have a point of inflection at x is equal to 0. For our right-hand curve, the quartic curve, when f double dash x is equal to 0, we have 12x squared is 0, and solving that x is equal to 0. Now, even though x is equal to 0 is the solution to f double dash x is equal to 0, it's clear that we don't have a point of inflection here at all. This entire quartic curve concaves up. So what that means is that just because we obtain the solution to f double dash x is equal to 0, it doesn't mean that our solution will guarantee us a point of inflection. So what we need to do is we need to do further verification of our result to make sure that our solution is in fact a point of inflection. There are two ways of verifying if a point is a point of inflection. The first is by using the first derivative f dash x. What we're looking for is we're going to be checking the signs of f dash x on either sides of x. And we want the sign to be the same to show that it's not a turning point. So here's an example. Using the same set of curves, on the left-hand side, we have the cubic curve. And for this cubic curve, f dash x is equal to 3x squared. So the point we're interested in is x is equal to 0. So we're going to be checking on either side of x is equal to 0. For simplicity, I'm going to choose x is equal to -1 and x is equal to 1. So I'm going to check what is the first derivative at x is equal to -1. So this is my formula. So we do some substitution. F dash -1 is going to be equal to 3 times -1 squared, which is equal to 3. And that is greater than 0, so it's positive. So we know that the curve is increasing to the left of x is equal to 0. Now, f dash x, that should be 0. So that's going to be 3 times 0 squared, which is equal to 0. So here we have got a stationary point. Now, f dash 1, subbing 1 into the equation, I've got 3 times 1 squared, which is equal to 3. Now, that's positive again, which indicates that the curve continues to rise. So you can see that we have got this behavior of the curve increasing, being stationary, and then continues to increase. So that means it's not a turning point. Hence, we do have a point of inflection at x is equal to 0. So here, yes, we do have got a point of inflection at x is equal to 0. On the right-hand side, our quartic curve, f dash x is equal to 4x cubed. So I'm going to repeat the same process, again checking either sides of x is equal to 0. For simplicity, we're going to choose -1 and 1. So do some substitution again. F dash negative 1 is going to be equal to 4 times negative 1 cubed, which is equal to negative 4. Now that's negative, that's less than 0. So the curve is decreasing on the left-hand side of 0. At x is equal to 0, f dash 0 would be 4 times 0 cubed, which is equal to 0, indicating that we have a stationary point. And f dash 1, that's me 4 times 1 cubed, which is equal to 4, which is positive. So that means that the curve is increasing. And if you look at that, what's happening is the curve is decreasing, it's stationary, and then it starts to increase. So this here is a behavior of a turning point, not a point of inflection. So in this second curve, for the quartic curve, we don't have a point of inflection at x is equal to 0. So this is how you use f dash x to verify if a point is a point of inflection or not. The second method to verify if a point is a point of inflection is by using the second derivative f double dash x. This time, what we want to do is we want to check the signs of f double dash x on either sides of x. Instead of requiring it to be the same, like in the previous example, this time we want the signs to be different on either side to indicate that there is a change in concavity. Using the same curves again, this time we've got f of x is equal to x cubed and f double dash x is equal to 6x. So we're going to complete this table again. So f double dash negative 1 is going to be equal to 6 times negative 1, which is negative 6. So that's negative, indicating that the curve concaves down at x is equal to negative 1. At f double dash 0, we have got 6 times 0, which is equal to 0. So here that's a possible point of inflection. At x is equal to 1, f double dash 1 is equal to 6 times 1, which is equal to 6, or positive greater than 0, indicating that the curve concaves up. So what we have here now is that we have a change in concavity going from negative 1 to 0 to 1. So that means here that we do have a point of inflection at x is equal to 0 for this curve. For the second curve, our quartic curve, f of x is equal to x to the 4, f double dash x is equal to 12x squared. So we're going to complete the table again. F double dash negative 1 will be 12 times negative 1, or in brackets square, which is 12, and that's positive. So the curve concaves up. At f double dash 0, that's 12 times 0 squared, which is equal to 0. So a possible point of inflection. And on the right-hand side of that, we have got 12 times 1 squared, which is 12 again. That's also positive. So the curve concaves up as well. So in this case, we don't have a change in concavity. On either side, the curve concaves up. So we can't conclude it's a point of inflection. In fact, this is not a point of inflection at x is equal to 0. So to summarize, to find the point of inflection, your first step, you want to solve for f double dash x is equal to 0. But this only gives you a possible point of inflection. After you get the result, you then need to check to verify if it is a point of inflection by using either the first derivative f dash x or the second derivative f double dash x. If you want to check using f dash x, you're going to be looking for f dash x on either side of x to have the signs being the same, to indicate that it's not a turning point. If you're using the second derivative f double dash x, you want the signs of f double dash x on either side of x to be different to indicate that there's a change in concavity. Once again, thank you for watching this video. I hope you learned something and found it beneficial. If you have any suggestions, please help us comment below. And if you liked it and found it helpful, please help us like it and share it. We upload videos every week. covering topics from Year 3 to Year 12 mathematics. So if you found it helpful, please be sure to subscribe. We'll see you next time. Bye.